Look around you. Every physical object in your immediate vicinity, from the concrete base of the nearest skyscraper right down to the glowing screen in your hand, began its life buried deep underground as raw material. Geologists refer to these materials as minerals. By definition, a mineral is a naturally occurring substance found in the Earth's crust that possesses a definite chemical composition and a specific set of physical properties. But digging up the raw materials is only half the equation. You also need power resources, the sheer physical energy required to run the heavy industrial machines, construct the infrastructure, and keep our homes lit. When you put these two necessities together, you realize that human civilization operates as one massive, ongoing extraction project. Our entire way of life relies heavily on a finite inventory hidden beneath the soil. The central tension of this extraction system is geographic. As this global map shows, nature distributed these essential minerals highly unevenly across the planet. The vast majority of this geological wealth is concentrated in specific borders, heavily favoring nations like China, the United States, Russia, and Australia. If we zoom in on the Indian subcontinent, we see this uneven distribution at a local scale. India holds immense wealth in heavy industrial staples, with massive iron deposits concentrated in Odisha and Jharkhand, alongside deep reserves of coal in Chhattisgarh. But to find liquid petroleum reserves, you have to look to entirely different regions, specifically trapped in Assam to the northeast and Gujarat out west. Because a nation's economic capacity dictates its standing on the world stage, and that capacity relies entirely on what it can dig up, countries are forced to rapidly mine whatever local resources they have before the well runs dry. To understand what we are actually digging for, we can divide these extracted materials into two primary groups. First, we have the metallic minerals. These are exactly what they sound like, materials that contain metals. They are physically hard, typically shiny, and act as highly efficient conductors of both heat and electricity. We break these down even further into ferrous minerals, which contain iron, like manganese, and non-ferrous minerals, which lack iron entirely, like copper and gold. The second group is non-metallic minerals. These lack metal entirely. Substances like limestone, mica, and gypsum fall into this category, but they remain strictly essential for mixing concrete and producing basic building materials. This photograph shows an open-cast mine, which is the easiest extraction method available. Miners use this technique when minerals sit close to the surface. It is relatively inexpensive, but it requires tearing open vast stretches of the landscape. For deeper deposits, operators must rely on shaft mining. This archival photo illustrates the dangerous alternative for reaching underground mineral veins, requiring workers to descend directly into the crust through deep vertical tunnels. And here we see a process called quarrying. This is a highly specific surface-level technique dedicated entirely to pulling raw building materials, like solid stone, straight from the bedrock. Whether an operation is scraping a shallow pit into a hillside or sinking a mile-deep vertical shaft, acquiring the basic hardware of modern society means continuously breaking apart the Earth's surface. But a mountain of extracted iron is useless without a way to forge it. We have to look at the conventional power resources required to operate the heavy machinery built from those metallic minerals. Look at this offshore platform. This specialized setup is required for drilling, the extraction method used exclusively to pierce the crust and tap into highly pressurized liquid fuels like petroleum and natural gas. For centuries, our energy grids have relied on these conventional sources: coal, petroleum, natural gas, and early large-scale tidal or water power. The fatal flaw of relying on conventional fossil fuels is time. They take millions of years of extreme geological pressure to form, making them strictly limited and highly exhaustible. Furthermore, the immediate consequence of burning these ancient, carbon-dense materials is the release of immense amounts of pollution. If a resource requires millions of years to create and heavily pollutes the air upon use, powering a growing, continuous future with it is a mathematical and environmental impossibility. Since humanity lacks the capability to artificially manufacture entirely new veins of iron ore or copper deep in the earth, our relationship with the metallic minerals we've already extracted has to change. The immediate step is conservation. This requires purposefully reducing material waste on the factory floor and upgrading industrial technology so we can output more infrastructure using fewer raw materials. As this historical salvage photo shows, recycling metals is an old idea, but today it is a mandatory economic strategy to keep previously mined hardware circulating permanently within the global supply chain. Pairing strict conservation with recycling protocols is the only viable way to break our reliance on single-use extraction, preserving what is left of our limited hardware for the generations that follow. And to solve the impending energy crisis, humanity has to stop staring down into the dirt for finite fuels and start looking upward toward non-conventional energy sources. These modern alternatives rely on continuously renewing systems, specifically solar and wind energy, alongside tidal power and advanced nuclear energy. This archival shot shows early adopters inspecting rooftop solar panels. Solar technology is highly critical because it scales easily, allowing us to directly harvest the sun's radiation without drilling a single inch into the ground. Similarly, as seen in this landscape of wind turbines, we can capture infinitely renewable mechanical energy simply by placing rotors in the path of the Earth's natural atmospheric currents. The advantages of these non-conventional sources are clear. They are inherently eco-friendly, they slash carbon pollution, and because they are driven by the mechanics of the planet itself, they will never run out. Ultimately, true economic development is no longer about how rapidly we can hollow out the Earth's crust. It is about how intelligently we can harmonize our infrastructure with its infinite renewable rhythms.